Okay. So before we get started today, I have some announcements. For reasons I cannot explain, Santa Fe is actually closed on the 2nd. UF isn't closing, but Santa Fe is. I don't understand it. I can't explain it. As far as I can tell, it is beyond comprehension. But those are the facts. So our exam is going to have to move. I talked with some people about maybe doing the test anyway since we're online, but the vibe is because we have like DRC students, we have students who would want to take the test in the library because their home computers or home internet isn't stable enough. For those sort of reasons, I'm not allowed to do it, which means that our exam 1 is being pushed back to 10/5, which is the following Monday. I'm not thrilled about this, but for you guys, it'll mean you have more time to study, so that's nice, I suppose. On the other hand, it means that next week I'm going to be doing less review and more like new material that's not going to be on exam 1, but you nevertheless need to pay attention to. So while it might sound like a good deal, it's not the case that we're just pushing back the exam and not doing anything else. We can't do that because there's only 15 weeks in the semester already. So we got to keep moving ahead. So this week, of course, as promised, we're going to finish section 7.4. I'll drop the study guide on Friday, but then rather than having the exam the following Friday, it will be the following Monday, like the Monday after that Friday. So this Friday, I'll give out the study guide, and then you'll have a week and 3 days to work on the study guide. But over that week, I'm going to be teaching you new shit that's not going to be on exam 1, so that kind of sucks. But we don't really have a choice. We got to do it like this, so this is the case, and I'm very sorry. But I wanted to update you, let you know what's going on. So yeah, that's what's going on. Today, we got 2 things. We're going to talk more about trig sub. And I would like to work problems that you guys want to see worked. So if there are any problems from the homework that you guys would like to see worked out, any trig sub problems, go ahead and type those numbers into the chat. And then the other thing that we're going to do is we're going to introduce section 7.4 on partial fractions. Sorry, I heard an ambulance coming to my neighborhood. Yeah, so this is the plan, okay? So any trig sub problems that you guys would like to take a look at from the homework? There's a lot of trig sub in there, some of it's pretty tough.
I haven't started like this homework yet because I've kind of been also reviewing like for the exam. But are there any like you could possibly pick out that we should be concerned about?
Sure, yeah, I have a handful of favorites. If everybody is kind of in that situation and nobody has any particular problems that they want to see, then Georgia wants to see 5 and 8. Yeah, I'd be happy to do either of those. The other problems that I would flag as being challenging here, 8's a little bit challenging. 7 is also quite challenging. The rest of those are fairly straightforward. So I think you'll probably be able to feel your way through them. Let's start with number 5. 5 looks like a good warm-up. We on homework 4 or homework 5? No, it was homework 5, right? Yeah, homework 5, number 5. So that's the integral of x squared square root x squared minus 9 over x cubed dx. So you have to look at this integrand and look at your trig sub Bible and ask yourself, what should I substitute here? If this was like 9 minus x squared, if the subtraction was in the other order, then I would substitute x equals 3 sine theta, because 1 minus sine squared is cos squared, so that would work out nice. If this was x squared plus 9, then I would substitute x equals 3 tangent theta, because tan squared plus 1 is secant squared, that would work out nice. But here it's x squared minus 9. My variable comes first before the constant.
So could you do 9 secant x?
So it's actually going to be 3 secant theta. So a couple things there, right? The number a here is always the square root of this number. I think of this as x squared minus a squared. So I'm going to substitute x equals 3. And then also we need to make sure we use a different variable inside the trig function than our original variable. I don't want to overload the variable x to mean two different things. So the substitution here is I let my old variable x be equal to 3 times secant of some new variable. You don't have to use theta, but I'll usually use theta unless there's a reason not to. So that's the substitution. And then I calculate my differential. Dx is going to be 3 times the derivative of secant theta, which is secant theta tangent theta d theta. And there's one other thing I like to put in this box. Since this is an indefinite integral, I don't need to change bounds, but I will need to go back to my original variable at the end, and that's going to require a little triangle. So I'll label a right triangle with one of the internal angles theta, and then I'll think about how I can complete that triangle using this information. If x is 3 secant theta, that means secant theta is x over 3. And remember, secant is the reciprocal of cosine. So that's the, cosine is the adjacent over the hypotenuse. So that's the hypotenuse over the adjacent. So I'll label my hypotenuse as x and my adjacent side as 3. And then if I complete this triangle to figure out the missing side here, I know that this squared plus this squared has to equal this squared. So this guy has to be the square root of this minus this, and it'll almost always be the square root from your integral. And it is here. So I like to tuck that triangle into my substitution box also, because I'm going to need him at the end to go back to my original variable. And by doing that right now, it'll kind of remind you what it is you have to do when you get to your answer in terms of theta. You're like, oh yeah, what do? I need to go back to x's. How do I do that? Thankfully, I've already drawn my triangle, so I can just go back and do it right away. So if I try to plug in this substitution now, everywhere there's an x, I'm going to write 3 secant theta instead. That means I'll have the integral of the square root of 3 secant theta all squared minus 9 upstairs. And then downstairs I'll have 3 secant theta all cubed. And then dx is 3 secant theta tangent theta d theta. Make sure you don't forget the differential stuff. For some reason, people often forget that in these trig 7 problems. And now we just have to simplify everything here as much as we can. And that'll give us a trig integral, like from section 7.2, and we'll grind that out. 3 secant theta all squared is 9 secant squared theta. So under my square root, I have 9 secant squared theta minus 9. Downstairs, 3 secant theta all cubed is 27 secant cubed theta. And then the 3 secant tangent still chilling. Make sure you don't slack on writing the argument of the trig function. Don't just write secant tangent, write secant theta tangent theta. Those are sort of mistakes that I have to take points off for on exams, so you want to develop those good habits now. The whole reason we're doing the trig sub is because of this square root. So the next thing I want to focus on is how to simplify and get rid of that square root. I can factor a 9 inside the square root. And what's left will be secant squared theta minus 1. Downstairs, I've got 27 secant cubed. So I can cancel the 3 into the 27 to get a 9. And then secant cubed and a secant upstairs, I can cancel one of those to get a secant squared. And then there's still the tangent theta d theta over here. Okay, is this going to be another one of those? No, it'll be a little different. Okay. Secant squared minus 1 under the square root is tangent squared. So that's the square root of 9 tan squared theta. Downstairs here, I still have 9 secant squared theta. And then over here is tan theta d theta. And now that I don't have any more subtraction or addition under my square root, I can go ahead and take the square root here. This is just multiplication. 9 times tan squared. Square root of that is 3 tan theta. Downstairs, of course, is still 9 secant squared theta. And then I had another tangent theta over here. So tangent times tangent, that's really a tan squared theta. So I've got tangent squared over secant squared. The 3 and the 9, those can pop out as a 1/3. But what do I do with this stuff? My advice would be to write as sines and cosines. So tan squared theta, that's sine squared over cos squared. And then we're dividing by secant squared. That's the same as multiplying by cos squared over 1. And you can cancel the cosine squareds. Everybody see that? So the sine squared over cos squared, that's tan squared theta from the top. And then secant is 1 over cosine. So dividing by secant squared is the same as multiplying by cosine squared over 1.
Can we pause real second so I can write it down real quick?
Sure, of course, yeah. And while Aisha is working, are there any other questions that you guys have? Anything else here that we want to talk about or anything else we're curious about?
In that final integral, that's sine squared, right?
Yes, sir. Yeah, coming from this tan squared. Sorry, it's a very little 2, but it is. It's a square. Any other questions here, guys?
Okay, I'm good.
All right. So then from here, we need to integrate sine squared, which is something we remember how to do from section 7.2.
Half-angle identities.
Exactly. So sine squared, I'll replace by 1/2, 1 minus cos 2 theta. So the 1/3 will become a 1/6. And I'll have 1 minus cos 2 theta. And then my antiderivative step here is not hard. 1 will integrate to theta minus cos 2 theta will integrate to sine 2 theta over 2. So my integral is equal to this. But I need to give the answer in terms of the original variable x. It's an indefinite integral. The theta piece here is not too hard to figure out. If secant theta is x over 3, then theta has to be the inverse secant of x over 3. But the sine 2 theta, he's a little bit harder. So remember that sine 2 theta, I can't read off the sine of 2 theta from this triangle. I could read off the sine of theta or the cos of theta, but I can't read off the sine of 2 theta. So I need to use my double angle for sine here to rewrite sine 2 theta as 2 sine theta cos theta. And the 2's will cancel. And now I can read off the result. So sine theta, according to my triangle, remember sine is always opposite over hypotenuse. So that's the square root of x squared minus 9 over x times cos theta is the adjacent over the hypotenuse. So that's just 3 over x. And now we're done. You could distribute the 1/6 if you wanted. You could write this as a single fraction if you wanted, but at this step, we are done.
Wait, can you go over that again?
So I did a few things here. I used the identity sine 2 theta equals 2 sine theta cos theta to rewrite this like this. And then I used my triangle to figure out the sine of theta and the cos of theta. All right, here's a triangle. It's a right triangle, and this angle is theta. So the sine of theta, according to like SOHCAHTOA, remember, is always the opposite over the hypotenuse. So sine theta is the opposite, which is the square root of x squared minus 9 over the hypotenuse, which is just x. So this piece is this piece. And cos theta is the adjacent over the hypotenuse. So cos theta is this piece. Is that making sense?
Yes.
Okay, so that's why we draw the triangle at the start. Because at the end here, this last little bit can be kind of confusing. And it's very possible to arrive at this line and then go, what the fuck do I do now? Right? Like, how do I go back to my original variable? It's easy to get a little bit overwhelmed at this stage. So if you draw your triangle right at the start, this serves as a nice reminder, like, how do I do that? Oh yeah, I drew that triangle at the start. That's the key. So I really do recommend setting up your trig subs for indefinite integrals just like this. Substitution in the differential over here, and then where you would normally put the bounds work, if this was a definite integral, for indefinite integrals, go ahead and put your triangle there. And that will remind you when you get to this step, what you need to do. You need to use the triangle to go back to your x's. Any other questions on this one, or comments, concerns, anything? Okay, so then number 8 was the next one we wanted to look at, and number 8 is a good deal harder. I'll write it down, but then I'm going to show you something in Canvas real quick. So homework 5, number 8. Your integral is going to look something like this. Okay, you might have something other than a 6 there, but it's going to look like this. And that definitely does not look like something from my trig sub Bible, right? That's not x squared plus a constant, or x squared minus a constant, or a constant minus x squared. What we need to do here is what's called completing the square. And you may or may not remember that, depending on how good your pre-calculus class was. So I'm going to show you something that I've put together for you guys in Canvas. This is you, so modules. If you go to the modules and you scroll down, so this is volumes of solids, 7.1, 7.2, 7.3. There's only one thing I've got in the trig subsection here, and it's this completing the square review. Read this document. Read it with a pencil and paper. Work along with it. Completing the square is an algebra trick. And one of the things it's useful for is proving the quadratic formula. So this serves as kind of an intro to completing the square. This outlines the whole process. But then here I've got lots of algebra examples. So the way you complete the square is you have to find this like magic number. The magic number is found by taking the linear coefficient, the number that's attached to the x, dividing it by 2, and then squaring the result. Then you add and subtract that number. So let me come back here. If I'm going to complete the square, I'll step off to the side and say, okay, I want to complete the square in x squared plus 6x. So I need to calculate my magic number. That's going to be 6 over 2 all squared, which is 3 squared, or 9. So I'm going to add 9 and then subtract 9. Now, having chosen this number correctly, the first 3 terms here will always factor as a perfect square, like x plus 7 squared, or x minus 2 all squared. In this case, it's going to be x plus 3 all squared. And then the minus 9 comes along for the ride. So this is my complete the square work. And that tells me that my integral is equal to the integral of x plus 3 squared minus 9. Like so. Nifty trick, right? Now this does look like something from my trig sub Bible. Here is u squared minus a squared. Remember when we introduced trig sub, I didn't use the letter x, I used the letter u, and I said that u could be any linear function of x. X plus 3 is a linear function of x. So the substitution I'm going to make here is u equals 3 secant theta. But u is x plus 3. So I'm subbing x plus 3 equals 3 secant theta, like this. If you wanted to, you could first do a little micro u sub. You could let u or z be x plus 3. And this would become the integral of square root z squared minus 9. Looks exactly like your trig sub Bible. But I think it's reasonable to do both at once like this because the differential on the left-hand side is so simple. The derivative of x plus 3 is 1. So here you just get dx equals 3 secant theta tangent theta d theta. And also I'm going to draw my little triangle. Here secant theta is x plus 3 over 3. So that's my hypotenuse over my adjacent, right? Because secant is hypotenuse over adjacent. It's the reciprocal of cosine. Cosine is adjacent over hypotenuse. So the hypotenuse on my triangle here is x plus 3. My adjacent side is 3. And this guy, if you calculate using Pythagoras, like this squared plus this squared equals this squared, this guy will come out to the square root of x plus 3 squared minus 9. The missing side of your triangle is almost always the square root from your integral. Okay, so there's my little substitution box. Now, if I plug in the substitution, x plus 3 is 3 secant theta, so this is 3 secant theta all squared minus 9. And dx is 3 secant theta tangent theta d theta. Now I'll clean up under my square root. That's the square root of 9 secant squared theta minus 9 times 3 secant theta tangent theta d theta. And within this square root, I can factor a 9. And what's left is secant squared theta minus 1. And then 3 secant theta tangent theta d theta. Secant squared minus 1 here is tangent squared. That's the whole reason I did this substitution. So my square root is going to become the square root of 9 tan squared theta
Can we pause 1 second after that? Because I couldn't see the triangle at a point.
Okay. Yeah, I can come back over here and zoom in a little bit on the triangle. I'll try to keep this in frame too. There we go. So based on my substitution, I divide both sides by 3 and I get secant theta equals x plus 3 over 3. Right here. And then I use the geometric definition of secant theta to interpret that as the hypotenuse over the adjacent. So I draw my right triangle and I label the hypotenuse as x plus 3. I label the adjacent side as 3. And then I solve for the missing side. This missing side over here should be the hypotenuse squared minus the adjacent squared. So he is the square root of x plus 3 squared minus 9. And that completes my triangle. Then I start plugging in for my substitution. So the x plus 3, I replace by 3 secant theta. And dx, I replace by 3 secant theta tangent theta, d theta. Squaring 3 secant theta gives me 9 secant squared theta. So my square root becomes 9 secant squared theta minus 9. The differential just stays the same through this whole process. I factor a 9 out inside my square root. So 9 secant squared minus 9 is the same as 9 times parentheses secant squared minus 1. And I do that because I know secant squared minus 1 is tangent squared. That's a Pythagorean identity. So again, the differential stuff over here stays the same, but I rewrite that square root as 9 tan squared theta. And now we're almost to the good part. Since I've gotten rid of any addition or subtraction under my square root's now just the square root of 9 tan squared theta, I can go ahead and take the square root. The square root of 9 is 3, the square root of tan squared is tangent. So I'll have integral 3 tan theta times 3 secant theta tangent theta. And if you did enough of the 7.2 homework, you'll recognize that this is a bitch of an integral. It really is. Because I've got secant to an odd power times tangent to an even power. The 3 times 3 can come out front as a 9. But then what's left is the integral of secant theta times tangent squared theta d theta. And that's a hard integral. That requires looping integration by parts. Thankfully, we've done that integral a few times. So I'm not going to burn the time right now going back through the looping IBP. I'll just remind you what the output is. The integral of secant times tangent squared is 1/2 secant theta tangent theta minus the natural log of secant theta plus tangent theta plus c. This is looping IBP. You pick u here to be tangent and dv to be secant tangent. So like I said, I'm not going to go through the looping IBP here. We've actually done this integral a few times in class. So if you don't remember how to do this guy, I recommend going back to either of the last 2 days where we talked about integration by parts. I think we did this both of those days. It involves running IBP with this choice of U and dV. You run IBP once, and then you apply a trig identity, and the integral loops. The upshot is you land here. So number 8, this is really a hard problem, right? You need to complete the square, then do trig sub, then do a looping integration by parts problem. It's not easy. But now that we've done all of that, we're ready to go back to our original variable. So I'll take a second here for questions or comments. Is my chat not working? I'm concerned. No? Okay, nothing there. There is a question in chat there. So Georgia asks, should we expect a problem like this on the test? Yeah, well, no. No, probably not. So certainly I could give you this integral on the test, or any looping integral. And I could give you a trig sub problem that requires completing the square. But I wouldn't do both in the same problem. I wouldn't hit you with both of those challenges in a single problem. I feel like that would be unfair. So while any of the components of this integral would be fair game, this whole problem would be a little bit harder than anything I would put on a test. But again, I could ask you to complete the square and do trig sub, or I could ask you to do trig sub and looping IBP, but I wouldn't put both of those into a single problem, okay? All right, so from here, we're almost there. I can see the light, you can smell the answer. My integral is 9/2 times secant theta tangent theta. Well, secant theta is the hypotenuse over the adjacent. So that's x plus 3 over 3. Tangent theta is the opposite over the adjacent. So that's the square root of x plus 3 squared minus 9 over 3. Minus the natural log of the absolute value of secant theta, which again is x plus 3 over 3, plus tangent theta, which again is that square root of x plus 3 squared minus 9 over 3. Close absolute values, close paren, plus c. So yeah, this one's a doozy. It really is. And that's why I wanted to make a point of doing this in class. I'm glad that Georgia requested it because, yeah, completing the square, trig sub, looping IBP, that's really quite a lot. And I wanted to make sure that I at least showed you guys how to complete the square once. Again, do look at the thing in Canvas here. Make sure you, you can skip the proof of the quadratic formula if you've seen it before, but if you haven't seen it before, this is very enlightening. A lot of people memorize this formula and have no idea where the hell it comes from. It comes from completing the square. But then definitely look at the reverse page, the algebra examples to make sure you're comfy completing the square, and then the calc example here to make sure that you're comfy with how we implement this in the setting of trig sub. Okay, so those were the 2 requested problems. I don't think there's anything else in there that's going to really give you a terribly hard time. Most of the trig sub questions that I selected are not terribly challenging besides that one. Number 8 we wanted to look at, did we do that yet? Oh, no, I'm sorry. This was number 7. Yeah, not number 8. So this one wasn't requested. That's right. This is my executive decision. So Georgia wanted to see number 8. We'll do that. And then we are going to move to talking about partial fractions. Before I leave this problem, this is my last call for questions on this guy. Make sure your notes are good. If you have good notes, you can always go back and look them over in case you get stuck. It's super important. That's the whole point, taking notes. So are there any questions here? Anything you would like to fill in? Anything you'd like to annotate? Okay, then. So I am going to move on. I'm going to do number 8 next, and then we're going to talk about partial fractions. Number 8's an interesting problem. At least the start of number 8 is interesting. So I apologize. I labeled that previous problem as homework 5, number 8. That was really homework 5, number 7. Number 8 is the one I'm going to do now. There's a randomly generated constant in the problem, but I'm just going to write it as x times the square root of 1 minus x to the 4. This doesn't look exactly like my trig sub stuff, right? It's not 1 minus x squared, it's 1 minus x to the 4. And there's 2 ways to attack this. Both require the same observation. Namely that x to the 4 is x squared squared.
What number is this again?
This is homework 5, problem number 8. The last one was problem number 7. I mislabeled it at first as number 8. But this is number 8. The last one was number 7. So looking at this, can anybody make a suggestion to get started?
Do a sub for x squared.
Yeah, we could do a little z sub for x squared. Then dz would be 2x dx. So if I make that substitution, x dx, that's 1/2 dz. So I'll get a 1/2 out front, and then integral square root 1 minus z squared dz. And that now looks exactly like one of my trig sub things. What should I substitute for?
Sine.
Good, I should let z be sine theta. Then dz will be cos theta d theta. And I should also draw my triangle at this step. So if z is sine theta is opposite over hypotenuse. I think of that as z over 1, right? Sine theta equals z over 1. So that's my opposite, and that's my hypotenuse. And then this side will be the square root of 1 minus z squared by the Pythagorean formula, right? Pythagorean theorem. So under that substitution, my integral will become 1/2 integral 1 minus z squared is 1 minus sine squared theta under the square root. And then my differential is cos theta d theta. Then I apply the Pythagorean identity to the piece underneath the square root. 1 minus sine squared is cos squared. And then my differential, cos theta d theta, still chilling. The square root of cos squared is cos. So this piece is cos theta, this piece is cos theta. So I end up with 1/2 integral cos squared theta d theta. And the way to handle that is with a half angle identity, remember? Cos squared I can rewrite as 1/2 times parentheses 1 plus cos 2 theta. So this 1/2 is going to become a 1/4 when I pop out the extra 1/2 that I get from that identity. And my integrand will become 1 plus cos 2 theta. So I'll have 1/4 integral 1 plus cos 2 theta d theta. And then the antiderivative step here is not hard. 1 integrates to theta plus cos 2 theta integrates to sine 2 theta over 2. And we saw something like this the other day. Can anybody tell me what the sine of 2 theta is from this triangle right away? Or is there something else I need to do with this first?
Shouldn't it be sine of 2 inverse sine z?
Yes, but I don't recommend that. Yes, you can say that theta is the inverse sine of z. And that's what we'll do for this piece. But for this piece, I want something more useful. So while what you said is correct, that would be the sine of 2 times the inverse sine of z, that's not at all useful. I have no idea what that looks like. So on the one hand, yeah, since z is sine theta, the inverse sine of z is theta, but also sine of 2 theta is 2 sine theta cos theta. That's the double angle identity for sine. And I can read sine theta and cos theta off as algebraic expressions from my triangle. So this is the trig identity I need to apply here in order to rewrite this term nicely. So this is 1/4, I'll write it as theta plus 2 sine theta cos theta over 2, cancel the 2's, and I'll get 1/4. Theta is the inverse sine of z, and there's no nicer way to write that. But sine theta and cos theta, those have much nicer expressions that I can read off from the triangle. Sine theta from this triangle is the opposite over the hypotenuse. That's z over 1. So this piece is just straight up z. And cos theta, I can also read off from my triangle. That's the adjacent over the hypotenuse. So that's the square root of 1 minus z squared. And this is really the best way to write this answer. It's true that this thing is equivalent to sine of 2 times the inverse sine of z over 2. But this communicates so much more than that. If you had to evaluate this between bounds for a definite integral, you sure as shit don't want to work with the sine of 2 times the inverse sine of z. That's a horrific looking expression that communicates almost nothing. But this is workable. This is just an algebraic function. This is relatively easy to understand in comparison. If you gave me the answer here as sine inverse z plus the sine of 2 times the sine inverse z over 2, I would take off a point on a test. I need to see that you know how to apply this identity and that you know how to use this triangle to go back to the original variable. That would still be 4 out of 5. You know, on my free response questions usually worth 5 points, that would still be 80% on the problem if you didn't make any other mistakes, but I would have to take that point off because it really is necessary to get back to this to understand what your answer really looks like. So again, we need to be very fluid with our trig identities. Those need to be like boom, 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 right there in your head. And I know it's not your fault that trig at Santa Fe sucks, but nevertheless, if I'm going to pass you through this class, I need to know that your skills are where they should be. And where they should be for a Calc 2 student is here. We need to be at a place where we can use these trig identities readily, where we can get back to an answer that makes sense and is workable with reasonable speed. So any questions about how we returned to the original variable here? Any questions from this line to this line, or about this stuff, or use of this triangle?
Do we need to go back to X?
We do. So if we're going to finish things up, we made a second substitution, right? The trig sub wasn't the only thing we did. So before we call it a day, my original question was given to me in terms of x. X is z squared. Sorry, z is x squared. So our very last step here would be to say this is the inverse sine of x squared plus x squared times the square root of 1 minus x to the 4 plus c, and that's everything done. Yeah, very good. But we're all comfy with using the triangle to go from thetas to z's. I think that's maybe the challenging piece here. If you haven't practiced this sort of stuff recently, let me grab a definite integral. There's one challenging definite integral in your homework that I would like to look at to get us a little bit more practice with this. It's the one that runs from 2 to 4. Oh, is that not in here? 2 to 9. We can do this one. Let's take a look at number 4. Well, we're going to decide how to split our time. Here we go, 15 minutes. Yeah, we'll do. All right. It's x squared minus 1. Yeah.
We can't see your screen.
I got you, thank you. So you're going to encounter a problem that looks like this at some point. And this is going to give us more practice with the actual trigonometry problem at the end. The substitution here isn't hard to spot. You've got x squared minus 1. And remember, the 3/2 power really does have a square root hidden in him. That's 1 over the square root of x squared minus 1 cubed. All right, that's what the 3/2 power means. It's 1/2 power and then the 3rd power. So my substitution here would be x equals secant theta. Dx then is secant theta tangent theta d theta. And my triangle isn't too terrible scary looking. If secant theta is x over 1, remember secant theta is the adjacent, or sorry, is the hypotenuse over the adjacent, because cosine is adjacent over hypotenuse. My hypotenuse here is x, and my adjacent side here is 1, which makes this side the square root of 1 minus x squared. What am I doing? I'm sorry. This is a definite integral, isn't it? So rather than drawing my triangle here, what I need to do is change my bounds. I'm sorry, and that's the whole reason we're doing this. So the sub here is x equals secant theta. Dx is secant theta tangent theta d theta. Yeah, I almost forgot why I chose this problem. When x is equal to 2, we have secant theta equals 2. Which means theta is the inverse secant of 2. Who knows what the inverse secant of 2 is? It's the same as the inverse cosine of 1/2, right? So for what angle between 0 and pi is the cosine of that angle equal to 1/2? It's up here at pi over 3. But at your upper bound, things are not so nice. When x is 4, you have secant theta equals 4, which means that theta is the inverse secant of 4. And there is no nice way to write the inverse secant of 4. Almost. So pi over 6 would be the inverse sine of 1/2, but we want the inverse cos of 1/2, or the inverse secant of 2, Jonathan. So what we have for our lower bound is pi over 3, but it's not obvious. Where is cosine equal to 1/4? That's not one that we know. That's not a nice value from my unit circle. So I'm just going to leave my upper bound as the inverse secant of 4. I'm sorry, 9. My upper bound here is 9. Inverse secant of 9. So my integral becomes the integral from pi over 3 to the inverse secant of 9. When x is equal to 9, we have secant theta equals 9. And then taking inverse secant on both sides, you get theta is the inverse secant of 9. So that's my new upper bound. My lower bound, when x is equal to 2, I have secant theta equals 2. So theta is the inverse secant of 2. That is a nice number. That's pi over 3. And now when I plug in the rest of the substitution, dx is secant theta tangent theta d theta. And downstairs here, I'll have secant squared theta minus 1 raised to the 3/2 power. So that's the integral from pi over 3 to the inverse secant of 9 secant theta, tangent theta over tan squared to the 3/2. The 1/2 power here will cancel with the 2, and we'll end up with tan cubed downstairs. So I get integral pi over 3 to the inverse secant of 9, secant theta, tangent theta, over tan squared to the 3/2 is tan cubed theta d theta. And so this is actually going to simplify to an integral we've seen several times. One of the tangents will cancel, and we get secant theta over tan squared theta d theta. And we saw this guy on Monday. Anybody remember how to handle secant over tangent squared?
You said
Change the sines and cosines.
Yeah, let's change to sines and cosines. And there is a way to get there with u sub, but there's also a much faster way. So secant is 1 over cosine. And then dividing by tangent squared is the same as multiplying by cos squared over sine squared. And you can cancel one of the cosines. And you get cos over sine squared. So I'll write that as cos theta over sine theta times 1 over sine theta, which is cotangent times cosecant. So you cancel a cosine, and you'll have cos over sine squared. I take that cosine and one of the sines, and then I leave the other sign down here. This is cotangent, this is cosecant. Integral of cotangent times cosecant is negative cosecant, because the derivative of cosecant is negative cosecant cotangent. So this is negative cosecant theta. I'll pop the negative out of my evaluation, and then I need to plug in pi over 3 and the inverse secant of 9. So we'll have here negative cosecant of the inverse secant of 9 minus cosecant of pi over 3. The reason I wanted to do this problem is because I have a feeling many of you haven't seen something like this in a while, if at all, because again, I don't trust trig at Santa Fe. You should have seen this sort of thing in trig. All right, these sort of problems, simplify this is one of the things that I would always put in a trig class, but I don't trust our trig professors to do that. So I want to remind you how to handle that sort of thing. It requires drawing a triangle. This piece, the cosecant of pi over 3, everybody should be able to sort out without a calculator. What is this? It's the reciprocal of the sine of pi over 3. Yeah, very good, Brian. The sine of pi over 3 is root 3 over 2. So this is 2 over root 3. That piece isn't hard. So this is negative cosecant of the secant inverse of 9. Distributing my negative, I get plus 2 over the square root of 3. So this is my only challenge. It's just a number, and it's not a horrible number to figure out, but you need to remember how to do it. So I'm going to leave my space here to write my final answer. I'm going to partition off some space here to do some work, just to find the cosecant of the inverse secant of 9. We let phi, or some angle, be the inverse secant of 9. In other words, I call this thing phi. You could use the letter theta if you wanted to. I just don't want to do that because I've used the letter theta elsewhere to mean something different. But the inverse secant of 9 is an angle, right? It's the angle such that the secant of that angle is 9. So we give it a name, call the thing phi. What I'm looking for is the cosecant of phi. So we want the cosecant of phi. And boy, wouldn't it be nice if I had a triangle whose internal angle was phi, because then I could figure out what the cosecant of phi is just from that triangle. Here's what I need to draw that triangle. Since phi is the inverse secant of 9, the secant of phi is 9. So I interpret that as 9 over 1, and remember secant is the reciprocal of cosine, so that's the hypotenuse over the adjacent. So I'm going to draw a little triangle here with internal angle phi, whose hypotenuse is 9 and whose adjacent side length is 1. Then, using the Pythagorean theorem, this squared plus this squared equals this squared, this guy has to be the square root of 81 minus 1, the square root of 80. So remember what you want. I want the cosecant of phi. The cosecant of the inverse secant of 9 is the cosecant of phi is the hypotenuse over the opposite, 9 over the square root of 80. So this piece is negative 9 over the square root of 80 plus 2 over the square root of 3. Can I just see, give me a thumbs up react if you've done anything like this in trig before, like sine of the inverse tangent of 5 or cosine of the inverse sine of 7, that sort of stuff. Just so I have a feel. I know it totally depends on who you took trig with. I promise I won't change things based on what you say here. I'm just curious. So it looks like we got maybe 5 people in total. Okay. So suggestions here. For more practice with this, you can make problems like this up really easily. Where do I have some space here? Yeah. For more practice, try to find the sine of the inverse tangent of 7. And B, how about secant of the inverse sine of 1/3. That sort of stuff. It's all the same. You're going to label this as like phi or theta. So then tan phi would be 7, which is 7/1. Draw a triangle, figure out the sine from that triangle. Same stuff here. Label phi as the inverse sine of 1/3. So the sine of phi is 1/3. Draw a triangle, figure out the secant of phi from that triangle. If you look in your modules, under the review material, the Paul's Online Trig review will have stuff like this under the inverse trig section. Right? Yeah, no, maybe not. Okay, so this is just the basics of inverse trig. So Paul doesn't actually have this stuff here. I would have thought he did, but I guess he doesn't. Yeah, no. All right. So my recommendation, at least these two. All right, spend a second at least crunching these two out. It's not going to be hard, and it's going to go exactly like I did over here. Do that so that you're comfortable with it, because something like this could absolutely show up on the test. And I guarantee you it will show up in your homework, not just here, but also down the line. All right. So with that out of the way, questions on this problem? Feeling mostly good? All right, how are we doing at time? Oop, we are out of time. Okay, so our intro to partial fractions is gonna have to wait till Friday, but that's okay because our exam, remember, has been pushed to October 5th because the school is closed on the 2nd. So next time we meet, I will talk with you guys about partial fraction decomposition, which is a totally algebra thing. It's not a calculus thing at all. But then we're going to use that algebra thing to help us figure out some calculus stuff. The material for the test will end in section 7.4. So this is not all the material for the test. The material for the test is going to go through partial fractions. So after Friday, you will have seen everything that's going to be on the test. And that's why I'll be releasing the study guide on Friday. All right, and then next Monday, probably we'll spend a little bit more time on partial fractions. Next Wednesday, I'm going to introduce material that will not be on the test. All right, so the material for the test cuts off this Friday. Promise you that. All right, our next meeting will be the last thing you have to worry about for exam 1. I'll release the study guide, and you want to start working on the study guide right away. Hand it in as soon as you can. That way I can give you some feedback. But then next week is going to be exam 2 material because we're going to have to push the exam. Yeah, and then the review will be next Friday instead of next Wednesday because the exam has been pushed, okay? So next Monday and Wednesday will be exam 2 stuff. And then next Friday, we'll review for the test. And then the test will be the Monday after that, October 6th. All right, as always, I have office hours today from whatever it says, 3:30 to 4:30. You can follow the link in Canvas. If you want to talk to me outside of those hours, send me a message on Canvas. I'd be happy to arrange a separate office hour, or you can send me photos of your work, all of those normal things. If you're having a hard time with any problems, please don't struggle with those on your own, and don't Symbolab or Bartleby or any of that shit. Much better to come talk to me or talk to a tutor or talk to somebody else. That way you're getting the experience of solving the problem, which is necessary to learn. So don't suffer in silence. If you're suffering, please come get some help. Otherwise, I will see you guys on Friday, okay? Alrighty, take care, guys.